Okay. Okay. Hello. Sorry, just let me check. Okay, let's start. Okay. Hello, everyone. I'm Wenjie. I'm a fourth year PhD student at NUS, supervised by Prof. Tra Tyson. And my research topic is about causal recommendation. So today my presentation title is called Causal Recommender System. Okay, maybe I just jump to the outline. Okay, this is the outline, and I will first introduce this work on counterfactual recommendation for mitigating the clickbait issue. And then there are some related works I have done recently. They are related works, so I just briefly introduce several of them. Okay, so let's start from the first work. Yeah, it's called Clicks Can Be Cheating, Counterfactual Recognition for Mitigating Clickbait Issue. And we all know that recognition has been widely applied in many online services, right? So clicks are the popular choice to indicate the user preference. So we always use some implicit feedback, for example, click or download or view to indicate the user preference as a positive sample to train the model, right? So clicks are popular to indicate the user preference. But the clicks have many problems. They have intrinsic bias and various issues. For example, users tend to click the items with attractive exposure features. Here we define the concept of exposure features. Exposure features means that the features of items are available before clicking the clicking action. And we define the content features as item features available after the clicking action. Okay, so the exposure features can be the title or the cover image of a video, right? So users tend to click the items with some attractive title or cover image. So we think they are interesting, so we just click, right? So this is our summer habit, I think. So this bias is also called attractiveness bias or caption bias in the previous work. And we find that there is some items, they will have the clickbait content. So it means that they will have some attractive exposure features, but boring content features. It can be called deceptive or misleading exposure features. So it will lead to the inconsistent click and certification. It means that even though we click, but we are not satisfied with the content. Yeah, this is the definition of clickbait issue. So it's common that a user is misled to click some items with clickbait content. So consequently, the recommender model will recommend these clickbait items frequently if we use click as a positive signal as to indicate the user preference, right? So it will have some negative effects. For example, it's unfair to some high quality video content. It can also hurt the user trust and satisfaction on the recommendation system. So so one solution is that can we use some post-click feedback, maybe the ratings or some user reviews to indicate the user preference. So as we know that why we choose click as the positive signal is because that they are easy to collect, right? So they are easy to collect in a large scale. But post-click feedback is hard to collect in a large scale because most of us will not give a rating after view a movie or micro video, right? So our motivation is that can we solve the clickbait issue by just using the click signals and without the post-click feedback as during training. So from this interaction process, we can find that the exposure features attracts users click, while the content features are disappointing, right? So we to achieve our target to solve the clickbait issue by using the clickbait, we utilize the causal theory. We try to disentangle the causal effect of these two features, the exposure features and the content features. we have known that the exposure features will attract users click while the content features are disappointing, right? So we aim to distinguish the effects of these two content features on user clicks. First, we propose a graph to describe the causal relations in this task. Here we can find that exposure features and E and content features T are fused to represent the item features. And then the user feature U and item features decides the prediction score. From this new figure, we find a shortcut from the exposure features to the prediction score. It means that it's because that an item can be directly recommended purely because it's exposure feature. For example, the attractive title. The prediction score can be high only because it's attractive exposure features. So the items with a clickbait issue can be easily recommended because this shortcut can cause a higher prediction score in the model output, right? So because of the attractive exposure feature. So our idea is simple, is to estimate the direct effect in this part, and we try to mitigate this effect during the recommender inference. So to estimate this natural direct effect, we conduct the counterfactual inference. It means that we can set several variables as the reference value and only estimate this remaining direct effect in this counterfactual word. It is shorted as a natural direct effect, NDE here. So it imagines what the prediction score would be if the item had only the exposure features. So the content features are blocked and only left the exposure features and in the effect of exposure features in this direct path. So we can estimate this kind of effect, and then for the clickbait issue, the items with the clickbait issue, they will have a higher prediction score in this direct effect because their exposure feature are attractive. And based on this attractive exposure feature, the prediction score could be high. And then during the recommender inference, we mitigate this kind of direct effect from the total effect, the original prediction of the recommender model. And then the item, maybe the clickbait item, for example, here, item 2, during its high prediction score in this direct effect, it will have a low score in the final ranking score. Yeah, we will use this indirect effect as a ranking score. Okay, this is the core idea of this method. And for the implementation, we propose a model agnostic framework because we can just model these relations based on different functions, right? So maybe we can train a different recommender to model these relations, and then we estimate the natural direct effect of E on Y, and we mitigate it during inference for ranking. So to implement that, we use the CTOCR backbone model to implement these relations. And actually, because the regular recommender model doesn't capture this direct effect, this direct parts in their design, in their implementation. So we add a separate branch to model this the effect on these parts, and we fuse these two parts into the final score, and then we can mitigate it during inference. Yeah, this is an implementation how to combine the existing recommender with this framework. Yeah. During training, we only use click for the parameter optimization, and during inference we mitigate this natural effect, this natural direct effect to reduce the influence of attractive exposure features. Yeah, this is about the implementation part. So any questions? If no, I just move on.
Yeah, I guess I have a very naive question, Wenjie.
Yeah, okay.
Could you please go back to page 7?
Okay. Yeah.
So forgive me, I don't have a very good knowledge on the causal graph. So for instance, for the illustration B, so the T here is the content feature and the Y here is prediction score. So Y here is not a shortcut from T to Y.
Yeah, a good question. Good question. Actually, it's similar, right? So if there is some direct effect from the exposure feature to the prediction score, it should have direct effect from the content feature to the prediction score, right? So it's similar things. Why we didn't model it is because we don't want to mitigate the direct effect of the content features during inference. We only need to separately model the direct effect of exposure features and mitigate this direct effect during inference. So this direct effect can be captured by these parts implicitly during the implementation. Yeah, so we didn't model it separately. If we want to do that, we can do that. Yeah.
Got it. Thank you. Thanks.
Yeah, this is a good question. Thanks for.
I think I also have a question. Oh,
yeah.
So I guess I didn't fully understand what exactly you're using as your exposure features versus your content features. Is it like an image processing of some sort, or yeah?
Yeah. For example, for the micro video data set, will have some title and cover image and have the video content, right? So we treat the title and cover image as exposure features. We use some text pre-trained language model to extract the textual features and use some pre-trained ResNet to extract the visual features. And for video, it has been extracted by the dataset platform. Yeah. So we just use them. Yeah.
Okay, that makes sense. Thanks.
Yeah. Actually, this is related to multimodal recognition, a multimedia recognition. They will use some item features for recognition. So it's not just use the item ID of the categorical features. It will use some multimedia features. Yeah. Yeah, this is okay. Any other questions? If no, I jump to the experiment part. Okay, thank you. Okay, so for the experiments, actually we because this is a model agnostic framework, right? So we use the COZR at 2021. I guess for now it's not a serious thought anymore. I think MMJSON is a JSON-based multimedia recommender model. Yeah, and we use news dataset and micro video dataset. For the news dataset, exposure features are the title and the short description, maybe abstract, you can understand, abstract. And for the content feature is news body, yeah. And for evaluation, we use the post-click feedback. We collect a small scale of post-click feedback for the testing. For the metric, we use a precision recall. It's just regular metrics. And for the baseline, we use two kinds of baselines. One is the training without post-click feedback. They have the similar, the same setting with our method. Sorry about that. And for the first one is normal training. Is normal training of the MMJSON, and the second one is only use the content features for training, because the exposure features can be attractive, but the content features are more reliable, right? So we can only use the content features for training. And the third one is IPW. Maybe you are familiar with this kind of method. And another one is training with post-click feedback. Training with post-click feedback means that we can use a small scale of post-click feedback during training. We can use them to identify the true positive clicks. So the click with satisfaction. And we can use some negative reweighting method. They can to reweight the negative samples. And the third one is re-ranking with using the click-like ratio. So it gives some it gives the items with higher like-click ratio a higher rank during the recommender inference. Yeah, it's a re-ranking method. So this is the overall performance. We can find that overall the methods with using the post-click feedback will have a better performance than the baselines without using the post-click feedback during training. And our proposed method, CR inference, can significantly recommend more satisfying items by mitigating the clickbait issue. It means that the click feedback can be better predicted during the inference. Yeah. This is a summer overall performance, and we also do summer in-depth analysis, I think. So maybe I just introduce one of them. This is we consider to do experiments about dataset cleanness. It means that we can filter out the noise clicks, right? Maybe we can decide the proportion of noise clicks during the training data. So we can find that this means that we have more noise clicks during the training and testing data. We can find that the test data is the same, and we only modify the training data. We can find that when we increase the proportion of the noise data, our method can have a better performance because they have more clickbait items, and the method can achieve better performance because it mitigates the clickbait issue. Yeah, and our method can achieve better performance than the baseline and the best baseline over different proportions. Yeah. Okay, this is about the first work. Any questions? If no question, I will just introduce briefly. I think I briefly introduce 4 works. I think maybe some of you will be interested in this topic, I think. So
sorry, before you go into it, I have a few more questions. Okay. Would you mind going back to the results that you had?
Yeah.
Yeah. So I guess I'm interested, maybe I just didn't understand. How do you calculate precision when you don't have post-click feedback?
When you don't have,
yeah. So if I understood correctly, what you're trying to really define when you don't use post-click feedback, you're just trying to predict whether someone will click on something. But when you do have post-click feedback, the precision is trying to predict whether that they actually liked it once they clicked on it. Is that correct?
It's similar, but a little difference. Because we use for ranking. So for ranking means that we for each user, we rank all the items they have never interacted with, right? And then we return the top K items to this user, and we select the top K items with a higher value, right? And this is the recognition list. And then we treat the items, maybe the items with positive post-click feedback as the positive samples, right? So maybe when precision means that when we have maybe 2010 top 10 recognition list, and if how many items in this list are positive items, if maybe two of them are positive, have positive post-click feedback, the precision is 20%.
Yeah. So my question is like, that's with the post-click, but if you don't have post-click feedback, then how do you define?
Okay. Yeah. Because our testing is based on the post-click feedback. Because if we don't have post-click feedback, we cannot find whether this method can achieve better performance on mitigating the clickbait issue, right?
Yeah. So you see how like your first, maybe I just not understanding how you defined the methods. But the first 3 methods, as they say, right, without post-click feedback, you mean you train them without post-click feedback, but then you evaluate them with post-click feedback?
Yes.
Okay. I understand. And so essentially, if I understand correctly...
It means that don't have post-click feedback during training. Yeah.
Okay. And then just to understand, I guess, like the underlying idea of why your model performs better is your... Essentially, you're better able to predict what they will actually like because you have kind of removed the kind of flashiness of something, the accidental clicks because it looked cool but wasn't. Okay,
Yes,
cool.
actually,
That's the interpretation.
Yeah, actually, because for each user, if the one item with clickbait content, because it has attractive exposure features, it will have a higher score, right? It will be frequently recommended. But if we mitigate the effect of the exposure features, and then it will be exclude out of the recognition list, right? Maybe so it will not be recommended. Yeah.
Okay, very cool. Thanks.
Okay.
Can I ask? Sorry.
Yeah. Yeah.
So I'm sorry if I don't understand, but like in your evaluation, in some way you're like, if something is it's a clickbait, so it's exposed more, it also has more chances to get more likes, right? So in some way,
Yes.
like that's what I like. I don't get, like, it's like how you counterbalance this, this bias that it's there.
Yes. I guess your question is that for some items, maybe they will have attractive exposure features, but it has a higher probability to be clicked and have a higher probability to have the positive post-click feedback, right? Yeah. Higher ratings, maybe higher ratings. It will have a higher probability to be clicked, and it will have a higher probability to be rated, to have a higher rating score, right? Because this kind of items are exposed more frequently. Is this your question? Yeah. Do I understand?
Yes. Yes.
Yeah. This is a good question. Yeah, actually, we also explained this situation in our paper. It's hard to evaluate. Yeah, it's hard to totally remove the exposure bias in this testing set. Yeah, we try to balance the distribution of different items. So maybe uniformly sample the items. Yeah, we all do such kind of experiments, but in this table we don't. We just do some additional analysis. Yeah, to analysis this kind of situation. Yeah, this is a good question. Yeah. So if no more questions,
sorry, I had another, but okay. It's going to be a very detailed question. But so how does this work for the TikTok dataset exactly? What is a click? And what is the post-click interaction?
Oh, I see. How to identify the post-click feedback, right? Yeah.
So I think you said it was a like, but then on TikTok you have this auto scroll thing. So what is a click then?
There are several ways to define a post-click feedback. Maybe, for example, like favorite, and retweet. These kind of actions can be treated as like. Also, there is a golden standard. It's called the duration type. So if you watch a video, the proportion is larger than a threshold, it can be treated as a like. Yeah.
And what is the click then?
Click is just
viewing of the, like when you see the video. Okay. Yeah. Okay.
Yeah. You'll see it is regarded as a click. Yeah.
Okay. Thank you.
Thanks for the question. So I just move on. Okay. This kind of I just briefly introduce the ideas, and for this work is called the causal intervention for mitigating the bias amplification. Yeah, bias amplification means that as I introduced before, the bias widely exists in the user feedback, right? Maybe for the user feedback, for each user, when we click their historical data, we can find that it's imbalanced with respect to the item categories. They will like some majority categories, and maybe in this case it's action movie, right? They will like many action movies, and the proportion of romance movie is small. And during recommendation, we can find that the model will tend to amplify this imbalance. So maybe more action movies will be recommended during this imbalance distribution. And such bias application is not good because it will intensify with time. It will limit the user view and causing some issues like field bubble. We think this kind of problem, this is one reason of causing for the field bubble issue. Yeah, so we also try to understand why this situation happens in the recommender model. Yeah, we find that the underlying reason is because the imbalanced historical interaction. We can find that the imbalanced historical interaction will affect the user reputation and also the prediction score. If one item is falls into belong to the majority categories, it will easily have a higher prediction score in the final ranking. And also the user reputation is close to the reputation of this kind of item. And we can find that this is actually a confounder issue. It confounds, it both affect user reputation and the prediction score. So we propose a backdoor adjustment. It's just an easy, an intuitive solution to solve this kind of backdoor adjustment issue, to solve this confounding issue. Yeah. And we also find some positive results for this is the performance with respect to the accuracy, and this is with respect to the biased application. We can find that this is a metric to measure how the bias is amplified. Lower value indicates better performance, and we can find that our method can achieve mitigate the bias amplification issue. Yeah. This is another work following the previous one. Actually, we also want to this is the previous work mainly introduce why the field bubble issue happens in the recommender platform, right? And this work we try to solve the field bubble issues by incorporating the user's controls. It means that we think for the field bubble issues, users should have the rights to control the field bubbles. If I like to stay in the field bubbles, I just receive this kind of recognition, right? If I want to jump out this kind of bubble, I can jump as based on the user's intention, right? So our proposal is that let user to actively control the field bubbles. It means that this is the original loop, the feedback loop between the user and the recommender model. Because in the outer loop, the recommender model will expose some items to the users, and then the users give feedback. The feedback are collected to retrain the model, right? This is the feedback loop. And we introduce another loop between user and the recommender models. It means that users can give control commands to the recommender platform, and the recommender platform can adjust the recommendations in real time based on the user controls. So this kind of system has three functions. One is that field bubble alert. It means that we define several metrics to measure the field bubbles and tell the users in current situation what kind of bubble in. And then we can alert the users if they are deeply in the field bubble for a long time, right? And then the second function is that we define several control commands. And by using these control commands, the users can adjust the recommendation list based on their intention. Yeah. And the third function is called real-time response to the user controls. So it means that the recommender model should be able to adjust the recommendation list in real time. And because if user adjust, we need to respond quickly, right? So we propose a framework to implement the controls and provide the real-time response. Okay, any questions?
I have a question. Can user make it worse, or
can
they only make it better?
Make it worse. It means we make the field bubble worse, right?
Yeah.
You give me more. Yeah, of course. We define the user choice based on the item features. So we can define an item to be more recommended or less recommended. Maybe for example, if user watch many action movies, they just want more. So it just adjust the some item attributes to be higher. Yeah, the values to be higher. Yeah.
I also have a question, which is,
yeah,
I guess I don't really understand, how do you define someone being inside a filter bubble? That seems like it would even be a complex question to begin with.
Yeah. We borrow some metrics and they design, I guess, let me think, one or two metrics. We borrow some metrics from the I don't say the study about political news. So they will design some metrics to measure how many maybe political news the user are borrowing, are watching. Maybe for some user, it's called ISO. I forgot his name. ISO index. Yeah, this is we borrow from another domain, and we also divide maybe summer coverage. Diversity related metric can also reflect the field bubble issues, right? This is about the diversity of the recommendation list, and this is based on the distance, the item distance. So if we watch many similar items, the item distances are very close. So we can use the distance metric to measure the field bubbles. Yeah.
And then I guess a follow-up question. So the ISO index, is it better when it's lower or higher?
Better is means lower field bubbles. Yeah. Lower means how to say? It's not a higher value index is not good. It will have severe field bubbles. Yeah.
So I guess what you're showing here is that you enable users to break out of filter bubbles in general. And so, yeah.
And achieve better accuracy because users are more satisfied. Yeah.
Okay, cool.
Yeah, this is based on some simulation experience, but a recent work, I guess, is a recent work have been used this idea in the real world industry platform. Yeah. And this is about the field bubbles for work. Any other questions? If no, I just move on. Okay, thank you. Thanks for the great question. Yeah. This is a work, I think a recent work. We are doing some research about OD generalization of recommender models. We guess that we all know this equation. It means that given a user and the item, we want to predict whether this user will like this item, right? So this is the objective of many recommender models, and is decided by, and this interaction process is decided by two factors. One is whether this item is exposed to this user, and another one is that whether if the item is exposed, whether this user will like this item, right? So only this item is exposed and the user likes this item, this user will interact and give a positive feedback with this item, right? Okay, this is the understanding the interaction process. Yeah. So it will have two kinds of shifts over time, we guess. One is that a shift of the recommendation policy. It means that if maybe in the first week, I recommend many popular items to this user, and in the second week, I recommend some unpopular items to this user. So the interaction distribution is quite different, right? So this is the first factor affecting the interaction distribution. And another one is the user preference. So maybe in the first week, I like some high price items. And in the second week, I like some low price items. So if user preference has some shift, so the interaction will also be have a different distribution, right? So this is a two kind of shifts. So to study the distribution shift in the user feedback is quite important because the user features and preference are always shifting over time. The user age is increasing and the environment is changing. So the user features are always changing and the user preference are dynamic over time. So if we use some historical interactions, the outdated interactions for the recommender training, and the performance will be not satisfying, right? So training with the outdated interactions will lead to dissatisfying recommendations in future environment. So we attribute the preference shift to the change of the observed or unobserved user features. It means that if the user income is increasing, so it will like some maybe more expensive items. If a friend this can be observed features. If we can observe some age or observe some consumption levels, maybe this kind of feature are observed, and also some unobserved user features. Maybe in some day, some friends recommend new items to this user. So these kind of factors cannot be observed, right? So the recommendation, the interaction distribution shift can also be caused by some unobserved user features. So for these two kind of situation, we design different solutions. Maybe I just briefly introduce the core idea. It means that we find that the user features, maybe the income, age, conformity. Now this kind of user features will affect the user preference. Maybe the user preference over price, user preference over brand, or user preference over some item category. And then this kind of preference will affect the final user interactions. Because I like it, so I bought it, right? So this is behind the logic behind this graph. Yeah. So for this, for the OD recommendation with observed user features, we can model the relations between this factor, right? If some of the factor is changed, we can infer the latest user preference and predict the new user interactions. Yeah, so the core idea is to how to figure out the mechanism how the feature shift affect user preference. Yeah, we propose two objectives for this OOD recommendation task. One is it should have a strong OOD generalization without using new interactions. So it means that if the user feature is changed in a new environment, we have no new interactions. We just use the observed user features to infer the latest user preference and the interactions. And the second is fast adaptation. It means that if in the new environment with in a new environment, the user feature is changed, and then we can use only a few of new interactions. We can achieve a better performance. It's called fast adaptation by using a few new interactions. To achieve these two objectives, we have three key considerations. One is that to figure out the relation behind this figure. And another one is we need to mitigate the effect of the outdated interactions, the historical interactions, maybe in the previous environments. And then we use some partial unchanged user preference to accelerate the adaptation. It means that for this, for the representation here, some user preference is changed, right? But some are not. Maybe we can reuse some of them to accelerate the adaptation. Yeah, this is the key considerations. Yeah, we just use for the method I just briefly introduced. Maybe we use some functions to model this Causal graph, to model these edges between these nodes, and then we mitigate the effect of the some outdated interactions by using the counterfactual inference. It's similar to the previous clickbait work, and we reuse some partial unchanged factors to accelerate the adaptation during fast adaptation, during this task, the second task. And this is the result of OOD generalization, and this is the result of fast adaptation. And this means that in the ID environment, how to do the evaluation. We just, for some user, we observe some user feature is changed, and then we divide the user interaction sequence into two parts. One, the previous one is called ID environment. The second part is called OD environment, and then we use the interactions in the ID environment for training and test it on the ID test and the OD test. And so we can find that for the OD environment, the performance will drop a lot from the ID to the OD environment. The performance will drop a lot, but our method can achieve better OD environment, OD performance with comparable, I guess it's comparable ID performance. Yeah, this one is better, but this is only comparable. How to define the user feature changes? Actually, we use 3 data sets. One is synthetic data set. For this one, it's easy, right? We just define some synthetic, define some relations between the variables, and we construct the data set. For Meituan data set, actually we use some user consumption level. Meituan have some user features for each user. They will recall them, and they will find that at a different time period, they will show different consumption level, and we define the user feature as the consumption level, and if the user consumption level increase or decrease, we define it as a OD environment. For Yelp, it's location changes. If a user changes its location, so the interaction will be totally different. Yeah. And this is a fast adaptation. It means that we give some OD interactions, the new interactions, we compare their performance. Yeah. Any questions?
Yeah, I have a question. I'm sorry, I didn't understand what you mean by IID or OOD.
ID means that if the interaction distribution is similar to the training distribution, it's called IID. Identical independent distribution, right? So if the interaction distribution is quite different with training distribution, and we call it OD environment. Maybe for this synthetic data, we just change the user features, and the user preference and interactions will change accordingly. And we define the interactions before the user feature change as ID environment. So we use this interactions for training and ID testing. And for the interaction after the user feature changes, we define it as OD interactions. We only use them as in this figure, in this table, we only use them for testing. And for this figure, we extract some of them for training. Yeah, it's called new interactions. Yeah.
Okay, I understood. Yeah, that's really cool. Thanks.
Yeah. Other questions? If no, I just move on. Okay, this is for the observed user features. So if we observe the user feature changes, and we can infer the latest user preference and interactions based on the changed user features, right? So if we don't, what if we don't know the changed user features? So this work solves the problem of OOD recommendation with unobserved user features. So if user feature is changed and we don't know that, we can only predict it. It means that we can only based on the temporal patterns, and we will predict what's the user preference will be in the next environment, right? Correct, right? So but the maybe sequential recommendation or session-based recommendation, they will use this kind of idea, right? They will model the pattern, the temporal pattern in the user interaction sequence. So what's the main difference between this work and the previous sequential based work. Actually, the main difference is that we assume the testing interaction are quite different with the training interaction. So it means that we can see for the first point, we can select some users. Their interaction have a significant distribution change over time. So we identify these users. It means that it must have some factors affect user preference, affects the user preference. So we identify these kind of users and we test the performance over these kind of users. These users will this out of distribution interactions will justify whether the model can have a better generalization performance, generalization ability. Yeah. So how to achieve that? The two key consideration is that one is that we need to predict the temporal shifts, and the second one is that we find that the user preference will sparsely affect the interactions. It means that the user preference can be summarized into several factors at the category level. It means that when I want to buy something, I only have several concepts, right? I only have some high-level preference over the item. Maybe I like some low-price item. I like one brand, and I like maybe some blue color. Maybe this is kind of a feature level or category level preference. And then I will to look up these items, and I bought one of them, right? So this is the motivation. It means that the user preference is can be categorized into several different category level preference, and this kind of category level preference will sparsely affect the interaction. Maybe the preference over seafood only affects the interaction with some seafood items. Maybe the preference over toy only affects the interaction with the toy items, right? So this preference will sparsely affect the interactions. And if some of the preference factor changes, and it only affect a subset of the interactions, right? So it's called a sparse influence. So if we can model this kind of sparse influence, when some preference factor changes, it only affects some of the interactions. The others are not affected, so the interaction prediction score are not affected, right? So our idea is that first we need to predict the temporal patterns, and for the second point, we need to disentangle the user preference, and then we model this sparse influence between user preference and the interactions. Yeah, this is a core idea. Yeah. Any questions? Yeah. Okay. So this is some results. We can find that for this is some sequential models. This is some disentangled models and some regular recommenders. And our method can achieve large over these users with large shifts. We can find that our method can perform better than the baselines by a large margin. And another interesting observation is that for these two data sets, we find it have large shifts. So it means that the testing interactions are quite different from the training interaction. And for this one, the shift is smaller. By observing this point, we find that for the sequential models, they perform better over these two data sets. And the disentangled models, they can perform better over this data set. It means that if the shift is high, we can use some sequential model to better model the temporal patterns, so they can have a better performance. And if the shift is not that large, maybe the disentangled models can have a better performance because it models the sparse influence between the user preference and the user interactions. Yeah. Okay. That's all. I just briefly summarize the work. I think we have done a series of work about causal recommendation. And we first start from debiasing, and then we consider some problems about maybe field bubbles, and then we consider the old generalization of recommender models. And in the future work, we guess for causality plus search or recommendation is a promising direction, and the more problems and tasks in this domain can be explored by considering the causal relation or causal modeling. And for example, the fairness, robustness, and explanation. For this, another direction is that the automatic causal discovery in complex scenarios. As we all know that for the causal discovery, currently we only do some research in synthetic data or some simple scenarios with few variables. So maybe for the complex scenario, it exists many unobserved confounder or colliders. Maybe for this kind of scenario, automatic causal discovery can be designed by considering the user interaction. Maybe user can give more signals to help us to discover the causal relations. Yeah, just some ideas. Yeah, naive ideas. Another one is the causal effect of recommendation. We also consider this direction because we have found that the exposed items actually has have some influence on the user preference. Maybe if the recommender model exposes many items to the user will gradually like it or hate it. Yeah. So this kind of effect can be studied in future work. We have started some work about political news because it's a serious problem, right? Maybe the platform have a higher influence. Yes, we are currently doing some work about in this direction. And lastly is a direction my supervisor liked it very much. It's called human in the loop. So it always tells us that you should consider users have a higher impact in your learning, in your recommended learning or model learning. So you need to consider let user give more signals to this platform and deeply interact with the end users. They will give, if they give some signals, it's more effective than the data, than the information you infer from the data. Yeah. Okay, that's all for today's talk. And this is my contact information. Maybe you have, if you have any questions or maybe collaborations, you can just contact me. Yeah. Thanks for listening.